Okay, 12.2. So this is the second part of testing more than 3 proportions at the same time. Okay, so in 12.1 we talked about the goodness of fit test. That's one type of test we can run on multiple proportions, but sometimes we want to test multiple proportions in a slightly different way than what we did in 12.1. So we're going to talk in this section about the homogeneity of proportions test, which turns out to be equivalent to something called the chi-square test for independence, okay? And so I'll do my best to explain those two tests and why they're really the same thing, okay? But the homogeneity of proportions test determines whether the proportion of subjects in various groups who have some characteristic are homogeneous, in other words, the same. To run this test, we first arrange the data into a contingency table, and we have some practice doing this because we've already looked at 12.3, right? Back when we were talking about testing 2 proportions. For example, it says Zocor is a drug manufactured that is meant to reduce the level of LDL cholesterol and increase the level of HDL cholesterol. Researchers were interested in determining what side effects are caused by Zocor, so they randomly divided patients into 3 groups. Group 1 received Zocor, Group 2 received a placebo, and Group 3 received cholestyramine, which is a cholesterol-lowering drug currently available. So it's basically like your, well, anyway. The proportion of patients who experienced abdominal pain in each group was recorded. The number of people in groups 1, 2, and 3 who experienced abdominal pain were 51, 5, and 16 respectively. The number of people in those groups who did not experience abdominal pain were 15, 32, 152, and 163. Arrange the data into a contingency table. Okay, so we have 3 different treatments, right? We have Zocor, we have a placebo, and we have cholestyramine. Oh, how do they spell this thing? Cholestyramine. Okay. And then within each of those treatment groups, we have some people who experienced pain, and then we have other people who did not experience pain. Okay, so this is how we arrange our contingency table. So now we just put the numbers where they're supposed to go. Okay, so for group 1, we were calling this group 1. Zocor, placebo was group 2, and cholestyramine was group 3. So for group 1, it said 51 experienced pain. For group 2, 5 experienced pain, and for group 3, 16 experienced pain. And then for the people who didn't experience pain, it was 15, 32, 152, and 163. Now looking at this, you may think, okay, this is bad news for Zocor because 51 of their patients experienced pain, and only 5 people who took the placebo experienced pain, and only 16 of the cholestyramine patients experienced pain. But look at the total number of individuals in each study. In the Zocor group, you had over 2,000 individuals in the study. In the placebo and cholestyramine groups, there were only about 200 in each of those. So of course, you're going to have a greater number of people with abdominal pain in the Zocor group. That's not really the question, right? The question is, what proportion of people in the Zocor group experienced abdominal pain versus the proportions of the placebo and cholestyramine groups, okay? But that's how you would arrange this into a contingency table. Once the data is arranged into a contingency table, we can compute the test statistic and so forth. The notation that we use in this section is the same as it was in 12.1. So OI is the number of individuals observed to have characteristic I. EI is the number of individuals expected to have characteristic I. And here, in order to calculate the expected value, it's kind of a complicated computation, but you would do row total times column total divided by table total. What do I mean by that? Well, the row total is the total number of people who experience pain. That would be the top row total. The bottom row total would be the total number of people who did not experience pain. Okay, and then the column totals are these vertical totals. So it's the total number of people in the Zocor group, total number of people in the placebo group, total number of people in the cholestyramine group. And then the table total is you just add up all of the numbers in the table, right? And that's your table total. So for example, if I wanted to figure out what is the expected number of people who took Zocor, like what number of people who took Zocor would we expect to have experienced abdominal pain, right? So what would the expected value be that corresponds to this observed value? And to calculate that, we would say, well, we would do the top row total times the first column total divided by the table total, okay? To get the expected value corresponding to this entry, we would do bottom row total times first column total divided by table total, right? And so forth, right? So that's how you would get the expected values there. Okay. So the homogeneity of proportions test. We're trying to see if these three proportions are the same. So notice that in 12.1, what we were trying to do is figure out, is P1 equal to this number? And is P2 equal to this other number? And is P3 equal to this third number? Or is at least one of them different? Whereas in this type of problem, we're not interested so much in what the proportions individually are. We just want to know how they compare to each other. We just want to know if they're equal to each other or not, okay? And consequently, the null hypothesis is going to be P1 equals P2 equals P3 equals P4, all the way up to however many proportions you're testing, okay? So the null hypothesis is that all the proportions are homogeneous. They're all the same, okay? The alternative hypothesis is that at least one of the proportions is different from the others, okay? The test statistic involves all these OIs and EIs. You feel kind of like old MacDonald, right? E-I-E-I-O. But yeah, it involves all these expected and observed values. You do these computations, you add them up, and this thing follows a chi-square distribution with this number of degrees of freedom. So it's the number of rows minus 1 times the number of columns minus 1. Like in this case, for example, you have 3 columns and 2 rows. So it would be 3 minus 1 times 2 minus 1. So 3 minus 1 is 2, 2 minus 1 is 1, so it would be 2 times 1. You'd have 2 degrees of freedom for this situation. You'd have 2 degrees of freedom. Anyway, once you have the test statistic, then you can compute the p-value. Of course, StatCrunch is going to do these 2 steps for us. And as always, if your p-value is small, you reject the null hypothesis. Same conditions to check in order to run this test as in 12.1, right? So all the expected values need to be bigger than 1, and at least 80% of them need to be bigger than 5, okay? Those conditions are pretty much always going to hold as long as the sample size is large enough, okay? And now to run the test in StatCrunch, you go to Stat, Tables, Contingency with Summary, and then you want to run the chi-square test for independence. This particular set of commands is similar to McNemar's test when we were testing 2 dependent proportions. We went to Stat, Tables, Contingency with Summary. The difference is that we then went to McNemar's test. And now we're going to do, instead, we're going to do the chi-square test for independence, okay? In order to run this test, you first have to enter the contingency table into StatCrunch just exactly the way that it looks, okay? Kind of like you did when we were doing McNemar's test back in 12.3, okay? So you enter the contingency table. You have to tell StatCrunch where your actual numbers are and where your row labels are, okay? Just like we did with McNemar's test in 12.3. So let me walk you through one of these. We'll finish this this cholesterol example, right? So Zocor is a drug manufactured that's meant to reduce the LDL cholesterol and increase the HDL cholesterol, right? Researchers, blah blah blah. They came up with these results. Right, we already walked through this example. It says, is there evidence that the proportion of subjects in each group who experienced abdominal pain is different at the 0.01 level of significance? Okay, so let's see. Groups 1, 2, and 3. The null hypothesis is that the proportions are all the same. P1 equals P2 equals P3. the proportion of what? Right? The proportion of people who experience abdominal pain. That's what we're really looking at. We want to know, is the proportion of people who experience abdominal pain the same in each group? Right? And the null hypothesis is that yes, it is. They're all the same. The alternative hypothesis is that at least one proportion is different from the others. Now, if you're trying to develop a little bit of intuition, then before we run the test, we could look at the sample proportions, right? You say, well, what proportion of people in group 1 experienced abdominal pain? That would be 51 out of 1532, right? So in P1, about 3.3% experienced abdominal pain. In group 2, that's the placebo group, it would be 5 out of 152. That, well, to 3 decimal places, that also rounds to 0.033. So I think those two at least are pretty similar. And then for the cholesterol group, it would be 16 out of 163. And that comes out to 0.098, so like 9.8%. That is pretty different from the other two. I would guess that we're going to reject the null hypothesis here, and that it's the cholesterol that's causing the rejection, okay? Because I think that probably the Zocor and the placebo were pretty similar. If that is the case, that's good news for Zocor, isn't it? Because that means that Zocor has developed a cholesterol medication that does not have abdominal pain as a side effect, whereas cholesterol, which is the already existing medication, does have abdominal pain as a side effect. Okay, that's what we would be able to conclude if we end up rejecting the null hypothesis here. So let's see if we reject the null hypothesis. We're going to go to Stat, Tables, Contingency, with Summary, and we want to run the chi-squared test for independence. I know that's a lot to write down. I'm really sorry, but hey, at least you're not having to do all of the math by hand. That would take pages and pages. Okay, so you just write down a little line to tell me where you're going in StatCrunch to get your answers. Okay, but this is where you would go. So let's do that. I don't know why I always try to minimize that, but okay. So the first thing we have to do is put this, put the contingency table into StatCrunch. So we had a row of people that had experienced abdominal pain, and then we had a row of people that did not experience abdominal pain. And the groups in question, some of them received Zocor, some of them took a placebo, and some of them took cholesterol. I'm just going to abbreviate that one like that. Okay, so we had 51, 5, 16, and 1532, 152, and 163. Okay, so there's our contingency table in StatCrunch. Okay, you can pause the video if you need to catch up, right? Of course, it should go without saying at this point. But let's run the test. So we're going to go to Stat, Tables, Contingency, with Summary. When it says to select the columns, it's asking you where are the actual numbers. In which columns do your actual numbers lie? And they lie in these columns, the Zocor column, the placebo column, and the cholesterol column, not the variable 1 column. The variable 1 column contains our row labels, right? So that's where our row labels are. And then we want to run the chi-square test for independence. That's the default setting, is for it to run that test anyway. Don't change it to McNemar's test, right? We want it to be the chi-square test for independence this time. So I'm going to hit compute. And there you go. You'll notice that it spits out the contingency table again, but then in addition to that, it also gives you all of the column totals and the row totals and the table total which is pretty nice. Most importantly, it gives us our p-value, which we can see now is so small, we're definitely rejecting the null hypothesis, right? But before I write that down, I just want to mention, you know, we calculated the sample proportions by hand. StatCrunch will do this for us. I always have to remind myself how to do this, but I think what we want, if I want to see what proportion of Zocor patients experienced abdominal pain, then I need to do 51 out of 50. Oh, and actually I did it wrong. I think when we did it by hand, we did it wrong. Shoot. Okay, because I think what I did when we did it by hand is I did 51 out of 1532. It should have been 51 out of 1583, right? I should have done the number of people who experienced abdominal pain out of the total number of people in the Zocor group. So I totally messed that up, and I apologize for that. But anyway, that's all right. We can get the correct values in StatCrunch now. But what I wanted to say before I realized that I made a mistake earlier, what I wanted to say is that in order to compute these sample proportions, we're going to want to do column percentages, right? We want what percentage out of this column experienced ab pain, what percentage out of this column experienced ab pain. So I'm going to compute the column percentages. And then what it does is it still gives us the counts, but then it gives us these percentages here, which is what we're after. So you can see that they are different than what we did because we did it wrong. But let me take you back to my calculator real quick, just so that I can prove to you that that really is the correct way to do it. I just wasn't thinking straight last time. So these things are wrong, but we could do them by hand, right? What we would do to do them by hand is we would say, if I wanted the sample proportion of people who took Zocor and experienced abdominal pain, I would say it's 51 out of 51 plus 1532. Right? That's what I would do. And then I get the 0.032 that StatCrunch gets. Right? 0.0322, right? And same thing with the rest of them. But anyway, so I kind of botched that one. I apologize. But the most important thing is our p-value here, right? So our p-value is 0.0006. And I guess another moral of that story is that if you're interested in getting the sample proportions, it's probably best to just let StatCrunch do that for you. Anyway, our p-value. Our p-value is tiny. It's less than our level of significance, which itself was pretty small, right? We were using the 0.01 level of significance this time, but still our p-value is smaller than that. So since that's true, we reject the null hypothesis, right? In other words, you're so sick of me saying this, I know, but I hope that my voice is in your brain when you're working on these problems in the homework and on the quizzes and on the tests, right? But in other words, what we're saying is that if we assume that all of the proportions are the same, then the probability that we would have gotten these results, 0.0006, which is really tiny, it makes us think that maybe this assumption is not true. So we reject it, okay? So at the 0.01 level of significance, the evidence suggests that the proportion of subjects in each group who experienced abdominal pain is different. Or maybe we can make that a little quicker. We can say, suggest that at least one of the groups has a different proportion of abdominal pain. That, you know, at least one of the groups, at least one group experienced a different proportion of pain. Okay, there we go. That would be a good conclusion. This is the kind of question that on a test or a quiz, I would be very likely to ask you some follow-up questions, right? Because if you don't look at these sample proportions and you just run the test, then all you're able to conclude at the end of the day is that at least one of the proportions is different from the others. But if you do look at the sample proportions, you can say which one is different. You can say, pretty clearly the cholesterol is the one that's different. And the reason that that's important is because you don't know, if you don't look at the sample proportions, then you don't actually know if this is good news or bad news for Zocor. Because it could be that one of the proportions is different. The proportion that's different is Zocor, and the proportion for Zocor is larger than it is for the other two, right? If you don't look at the sample proportions, then that's totally a possibility in your mind. And so that would be very bad news for Zocor. But that's not what actually is the case. And you can tell that by looking at the sample proportions. So on a test or a quiz, I would be very likely to ask you a question like, you finish this problem, then I would say something like, is this good news or bad news for Zocor, right? And then your answer would be, this is good news for Zocor because their sample proportion was a lot lower than the sample proportion for cholesterol. So Zocor is most likely not causing abdominal pain, whereas cholesterol does. Right? So it's good news for Zocor. Anyway, so that's that one. So that's a homogeneity of proportions test. Now I said at the beginning of this lecture that homogeneity of proportions is equivalent to a test for independence. And in fact, when we ran the test in StatCrunch, we went to chi-square test for independence. So how is it that a homogeneity of proportions test is the same as a test for independence? Well, if there's no difference in the proportion of patients who experience abdominal pain between the medications, then the variables abdominal pain and medication are independent. Let me say that a different way. Okay, so another way to say that is if the type of medication that you take doesn't affect whether or not you experience abdominal pain, then abdominal pain and medication are independent variables. That's just the definition of what it means for variables to be independent, right? The probability of one occurring doesn't change the probability that the other occurs. So if changing your medication doesn't change the probability with which you will experience abdominal pain, then abdominal pain and medication are independent, right? Well, in that case, the proportion of patients taking each different kind of medication would be the same, right? If the medication doesn't affect whether or not you experience abdominal pain, then the proportion of patients who experience abdominal pain is going to be the same in each group. So in other words, saying that the proportions are all the same is the same thing as saying that the variables in question are independent. Okay. Now, on the other hand, if there is a difference, right? If people taking cholesterol experience abdominal pain at a much greater proportion than people who take Zocor, then clearly the type of medication has an effect on whether or not you experience abdominal pain. And that means that medication and abdominal pain would be dependent variables. So if there is a difference in the proportion, then the variables are dependent. Okay. And that's why homogeneity of proportions is the same thing as testing for independence. Okay, testing to see if the proportions are homogeneous, or in other words, if the proportions are all the same, is the same exact thing as asking yourself if the variables are independent. We like rephrasing homogeneity of proportions in terms of independence because it makes things a little bit more generalizable. Okay, so let's take a look at a couple of examples. And by the way, if you're confused by what I just said, please rewind the video, rewatch that section of the material where we're describing this little paragraph here. It's important, okay? Try to understand it. Do what you need to do in order to understand that, okay? But here we go. So if we're running the test as a test for independence, then we're going to state the null and alternative hypotheses a little bit differently, even though it's really the same test that we're going to end up running. So if we want to state this as a test for independence, then we're going to say variable 1 and variable 2 are independent, and the alternative is going to be variable 1 and variable 2 are dependent. And it's always that way. The null hypothesis is always independence. The alternative is always dependence. Okay, always, always, always. Don't get those mixed up. I can tell you right now, about half of my students in past semesters will mix those up. Don't mix them up. The null hypothesis is independent, always, right? The alternative is dependent, always, okay? Well, let's take a look at some examples now. So example 2 says, in a study of 1,000 randomly selected deaths of men aged 45 to 64, the cause of death, along with the victim's smoking habits, are listed. Is smoking independent of cause of death? Test the 0.05 level of significance. Well, so let's see. The null hypothesis is that smoking and cause of death are independent. They have nothing to do with each other, right? What we're trying to do is show that there's a link between smoking and cause of death. So that's going to be our alternative hypothesis. There's a link between them. In other words, they're dependent, right? So smoking and cause of death are dependent. Okay. So let's run the test. All right, we're going to go to stat, tables, contingency with summary, and we want to run the chi-square test for independence. Right, that's exactly what we're trying to test for. Okay, let's see what we get. So first we have to enter the contingency table, of course, right? So we have a group of smokers and we have a group of non-smokers. And we have what they died from, like cancer, heart disease, and some other cause, right? And by the way, it's just a coincidence that that both of these examples that we've done have been 2x3 tables. You could have a table that's, you know, 2x5 or 3x7 or 3x4 or whatever, right? But anyway, you still run the example the same way. Whoops, 140. Okay, so let's do it. Stat, tables, contingency with sum. It says select columns. It's asking you, where are your numbers? My numbers are in the cancer, heart disease, and other columns. And it says, where are your labels? Well, my labels are in the variable 6 column. Okay. I want to run the chi-square test for independence. I might be interested in looking at some column percentages. Then again, I'm not exactly sure. I might want row percentages here or percent of total. I don't really know. But we'll play around with some stuff. Okay. Tiny p-value. We're rejecting the null hypothesis for sure, right? Which means that smoking and cause of death are dependent variables. So another way to say that is that your cause of death is dependent on your smoking habits, right? Anyway, looking at the percentages, we can see that if you're a smoker, well, hold on a sec. Maybe what we really want is, well, so if you died of cancer, so basically it's saying, in this particular study of men aged 45 to 64, 55, so 28, almost 29% of the men who died of cancer were non-smokers, and 71% of the men who died of cancer were smokers. So that's a pretty clear indication that, you know, smoking can increase your risk of dying from cancer. Then again, that's maybe not a great way to look at this, because I think the total number of smokers, the total number of smokers was 650. The total number of non-smokers in the survey was 350. So of course these percentages, all of these percentages down here are going to be smaller than all of these percentages up here. So maybe we don't really want to look at the column percentages. Maybe what we want instead are the row percentages. That might be a little more illuminating, right? Yeah, this is more illuminating because this gives you a breakdown of smokers versus non-smokers. So if you're a smoker, there's a 20.8% chance you die of cancer, a 47.7% chance you die of heart disease, and a 31.5% chance you die of something else. Whereas if you're a non-smoker, then there's a slightly smaller risk of dying from cancer, and a slightly smaller risk of dying from heart disease, which means there's going to have to be a bigger chance of dying from something else, right? But yeah, I like the row percentages a little bit better on this one for making sense of the data. But anyway, no, the p-value is so small. Like, no, the cause of death is not dependent. It is not independent of smoking habits, right? They're dependent variables. So since our p-value was 0.01, what was it? 0.0154. 0154. Yep. So since 0.0154 is less than 0.05, we reject the null, okay? At the 0.05 level of significance, the evidence suggests that cause of death is dependent on smoking habits. Okay, so that's that. You can hear my family listening to the Hamilton soundtrack in the background, maybe. Everyone has, you know, everyone gets to just party and have fun in my house, except me. Here I am slaving away recording these dang videos. But that's that one, okay? So, by the way, another way to word the conclusion is you could say the evidence suggests that cause of death and smoking habits are dependent variables. Okay, so that's another way that you could state the conclusion. Okay, let me give you another example of this. Oh, no, I'm going to give you a summary of what we've talked about in chapter 12. This is good. Because in total in chapter 12, we've talked about 3 different tests, but really, these 2 are the same. They're the same test, just a slightly different perspective. So really it comes down to 2 tests, right? The goodness of fit test, which we did in 12.1, and the homogeneity of proportions / test for independence that we did in 12.2, okay? But the reason I'm listing them as 3 different tests is because you state your null and alternative hypotheses differently if you're running homogeneity of proportions versus a test for independence, okay? But you go to the same place in StatCrunch to run these 2 things. I think the test for independence is pretty clear how it's different from the others. But if you look at goodness of fit versus homogeneity of proportions, this is where students sometimes have trouble distinguishing between the 2 tests. I think the biggest difference between them is that in the goodness of fit test, you have an actual number that you can say P1 is equal to that number, P2 is equal to some other number, P3 is equal to some third number, right? Whereas with the homogeneity of proportions test, you don't have some kind of previous or prior value to compare your proportions to. So you're not comparing each individual proportion to some number. Instead, you're comparing all of the proportions to each other, okay? And you can see that clearly when you look at the null hypotheses and how they're stated, okay? So, so take some time and make sure you look at these and that you really understand the difference between these three tests. I'm going to run you through a whole bunch of examples now. I'm not going to run the test, right? So I'm just going to state the hypotheses and make sure that I can get us set up running the correct test, but then I'm not actually going to run the test. And I'm going to take you through an example of all of the different kinds of proportion hypothesis tests that we've talked about starting in chapter 10, so that hopefully you can see the difference between some of these things, right? And again, I'm not interested so much in the conclusion of these tests. I just want to make sure that we can set them up correctly. This one says, determine which kind of testing to use. State the hypotheses. It says, in 1994, a survey asked children, do you like unicorn giggles? 79% answered yes. A new survey asked children the same question. Of the 45 children surveyed, 34 answered yes. Have children's opinions about unicorn giggles changed since 1994? Okay. Here, we're only testing one proportion, the proportion of children who like unicorn giggles. And what we're trying to test to see is if that proportion has changed since 1994. Well, the null hypothesis is that it has not changed since 1994. It's still the same as it was in 1994, right? Which is 79%. The alternative is that it has changed, okay? So this is a one proportion hypothesis test. We go stat, right? Proportion stats, one sample, right? And then you would feed it the number of successes, the number of observations, right? There were 34 successes out of 45 observations in this particular study. So you can get the p-hat value to see if it seems different from 79%. 34 out of 45 is 75, 0.756-ish. So it seems to have gone down a little bit. Is that difference enough to reject the null hypothesis? Well, you have to run the test, right, to find out. But that's that, right? So this is a single hypothesis test. Sorry, a single proportion hypothesis test. Now let's look at part B. It says, a survey of children asked, do you like unicorn giggles? Of the 35 children aged 3 to 6 years old, 27 said yes. Of the 32 children aged 7 to 10 years old, 15 said yes. Does the sample evidence indicate a difference in the proportion of children in each age group who like unicorn giggles? Okay. Now, notice in this example that you don't have any kind of prior estimate for like what proportion of 3 to 6 year olds like unicorn giggles and what proportion of 7 to 10 year olds like unicorn giggles. So you're not going to say, you know, 3 to 6 year olds is group 1, 7 to 10 year olds is group 2. So you're not going to say, let me label those before I go further. But you're not going to say P1 equals, you know, 13% and P2 equals 17%. You're not going to say that, right? Because you don't have that information. The best you can do in this case is just to compare these two proportions to each other. And that's exactly what you're prompted to do anyway, right? It says, does the sample evidence indicate a difference in the proportion of children in each age group who like unicorn giggles? So you just want to compare the age groups to each other, right? So you just want to compare to see, is the proportion of children who like unicorns in group 1 the same as it is in group 2, or are they different? Okay, so this is a 2 proportion test instead of a 1 proportion test. Now, when you have 2 proportion tests, you have to ask yourself if the samples are independent or dependent, because the test that you run is going to depend on your answer to that question. In this case, the samples are independent, right? You can tell that a couple of different ways. You know, for one thing, if the samples were dependent, then they would be matched pairs. And so then your sample sizes would have to be the same. But Here, the sample size of 3 to 6-year-olds is 35, and the sample size of 7 to 10-year-olds is 32. So clearly, they're not matched pairs. But more importantly, there's nothing in the question that says anything about them automatically determining group 2 based on how they determined group 1. Right? It's not like they did brother-sister pairs or husband-wife teams or something. Well, you wouldn't do husband and wife, I guess, if you're talking about 3 to 10-year-olds. But no, they don't have any way to match these kids up. They just randomly selected a group of 3 to 6-year-olds, and then they randomly selected another group of 7 to 10-year-olds. So these are independent samples for sure. So if you're testing two proportions and the samples are independent, that's when you go to stat, proportion stats, to sample. Okay, and then of course you have to enter the number of successes and number of observations for each group and so on and so forth. Okay, but I'm not interested in actually running the test. I just want to make sure we can set it up correctly. So that's that one. Okay, so by the way, this was we covered this in 10.2. We covered this in 11.1. Okay, moving on. Part C says, in 1994, more unicorn giggles. Okay, in 1994, a survey asked children on a scale from 1 to 5, how much do you like unicorn giggles? 12% responded 1, 6% responded 2, 3% responded 20. 3% responded 3, 22% responded 4, and 57% responded 5. That was in 1994. Okay, a new survey was conducted asking the same question. The results of the survey are summarized in the table below, right? So this table right here. And now the question, have children's opinions about unicorn giggles changed since 1994? Well, the null hypothesis is that no, they have not. They're the same as they were in 1994. So if that's true, then the proportion of kids who answered 1 would be the same as it was in 1994, right? 12%. The proportion of kids who answered 2 is the same as it was in 1994, 6%. 3, same as 1994, same as 1994, same as 1994. Okay? That's the null hypothesis. The alternative hypothesis is that at least one of these proportions is different than claimed in the null hypothesis. Okay? Okay? This is a goodness of fit test. If you look at the previous page, you're not talking about homogeneity of proportions. You're not comparing each proportion to each other. You're comparing each individual proportion to some past value, okay? Which is exactly what we're doing here, okay? So this is a goodness of fit test, so you're gonna go to stat, goodness of fit, chi-square test, okay? And that's that one. These values right here are your observed values. So you're going to enter those into an observed column. And then these values right here are your expected values. You're going to enter them into an expected column. And then run the test in StatCrunch. Okay? Here's another example. It says, a survey was conducted asking children, do you like unicorn giggles? Their responses are summarized in the table below. So we have some kids that like them, some kids that don't like them. We have different age groups. It says, does the sample evidence indicate a difference in the proportion of children in each age group who like unicorn giggles? Okay, is there a difference in the proportion in each age group who like unicorn giggles? Well, we don't have any past observations to compare these new observations to. So we're not going to say, if I call this group 1, group 2, group 3, and group 4, we're not going to say P1 equals, 0.12 and P2 equals whatever. We're just going to compare the groups to each other, right? So the null hypothesis is that the proportions are all the same. the alternative hypothesis is that at least one PI is different from the others. Okay? So this one is a homogeneity of proportions test. Okay? To run that test, you go to Stat, Tables, Contingency with Summary, and then you run the chi-squared test for independence. Okay? So that's that one. Hopefully you can see the difference between parts C and part D. By the way, this was 12.1. This was 12.2. And now let's see one more. It says a survey was conducted asking children, do you like unicorn giggles? Their responses are summarized in the table below. Does the sample evidence indicate that liking unicorn giggles depends on age? Ah, okay. So now they're asking us to run a test for independence, right? The null hypothesis here is going to be that liking unicorn giggles and age are independent. In other words, your age does not affect whether or not you like unicorn giggles, okay? That's the null hypothesis. Then the alternative hypothesis is that liking unicorn giggles and age are dependent. Okay. Now then, to run the test, it's Stat, Tables, Contingency with Summary, and chi-squared test for independence. So it's just exactly the same as what we wrote down on the previous one. The StatCrunch prompts anyway are exactly the same. It's just you state the null and alternative hypotheses differently. Okay, that's the only difference there. But as we discussed earlier in this section, they're really exactly the same test. You're going to get the same p-value. You're going to make the same decision, right? You're just going to state these things a little bit differently because here they were asking you if all the proportions were the same. And here they were asking you if the variables were independent. So you should state your null and alternative hypotheses appropriately so that you're answering the question. By the way, this was also 12.2. Okay. So that's that. The rest of these problems, I think I'm going to skip for now. I might come back and do these as part of a review or something. If you know, when we're reviewing for your last test, which is coming up in like a week or something. So it's coming up pretty soon. But for now, I'm going to skip them. That's all I'm going to say. I might come back to this later. Here's your homework assignment. There might be a couple problems that ask you to do something like construct a conditional distribution. What they're asking you to do is to construct a relative frequency distribution for each category of the data. So kind of like when we looked at the row percentages and column percentages, like on this problem right here, if they asked you to construct a conditional distribution, all you would do is change these to percentages, change all these numbers to percentages. And the percentages should be column percentages. So you can even use StatCrunch to do it, right? So that's what they mean by that, okay? And that does it for 12.2.